Hello again, this is Dr. Hanaa Assil, and this is another video for the AS Chemistry at Excel. We're talking about organic chemistry, so let us take a look at what we know from the O-level course. We already know what are organic compounds. You should know that organic compounds are covalent compounds of carbon that were originally obtained from plants or animals. So all of these are compounds of carbon. They are all covalent compounds. You remember what is covalent? They're sharing electrons, and they were originally obtained from plants or animals because they were originally obtained from petroleum, which is obtained from plants and animals. So we talked already in O level about alkanes, alkenes, alcohols, carboxylic acids, and so on. Hydrocarbons are organic compounds made up of only carbon and hydrogen. So this is one type of organic compounds in which the compound has only carbon and hydrogen. So we know that alkanes are hydrocarbons. Alkenes are also hydrocarbons. They all have carbon and hydrogen only. Okay, we also know from O level that we have groups of organic compounds which we refer to as homologous series. So the homologous series are groups of organic compounds that have the same general formula, and we said general formula means in general how many hydrogens do we have related to carbon. So we should remember from O level that the general formula for alkanes was CnH2n plus 2. That means if I have an alkane, the number of hydrogens are twice the number of carbons plus 2 hydrogens extra. The alkenes have a general formula of CnH2n, so the number of hydrogens in an alkene is twice the number of carbons. So, homologous series like alkanes, all the members have the same general formula. They also have the same functional group. So we said all alkanes have only single bonds between carbons, and alkenes, for example, have a double bond between carbons. So these are the functional groups. And all the members of the same homologous series have the same chemical properties. So when we talk about alkanes, they all do the same general types of reactions, and alkenes all do the same reactions. Okay? Now, when we look at organic compounds, you should realize that organic compounds will differ, first of all, in the length of their chain. That means in the number of carbons. And that affects the physical properties of the compounds. So you should realize that a compound that has a short chain or a small number of carbons would be gases or liquids with low boiling points. So alkanes, for example, that have 1 carbon, 2 carbons, 3 carbons, 4 carbons, all of these are gases. So a small chain or a small number of carbons are gases. Now, longer chains or more number of carbons would be liquids, and even more would be solids. Also, if I'm comparing, the longer the chain, the higher the boiling point. So if I have a small chain like C2H6 that has only 2 carbons, this will have a lower boiling point than something that has more carbons like C5H12. Also, another point that will differ in the boiling point is whether I have a straight chain or a branched chain. Straight chain means all the carbons come one after the other. So for example, that first structure is a straight chain for pentane that has 5 carbons. But I can also draw the pentane in a different way, 5 carbons also, but 4 of them in a chain, and 1 of them is what we call a branch. So that CH3 on top there is called a branch, and you should realize that a straight chain compound will have higher boiling points than if it is the same number of carbons but branch. So remember that if it is less carbons, lower boiling. If it is more branching, same number of carbons but more branching, then that would be a lower boiling point. So for example, if we look at this, these structures show carbons and they indicate different number of carbons, and you should realize that if I have a longer chain like the one in D, that would have the highest boiling point. Now, another thing that determines the differences between compounds is the types of bonds. So we know that if we have only single bonds between the carbons, then we call that saturated. So for example, alkanes are referred to as saturated organic compounds. And if we say why we say they are saturated, this is because they have only single bonds between the carbons. Single covalent bonds are usually strong, they are difficult to break, so any saturated organic compound is usually less reactive or unreactive compared to something that has a double bond. So if an organic compound contains double bonds between the carbons, this is referred to as unsaturated. So ethene here, for example, is unsaturated. And you should realize that a double bond will be very reactive, and that means that it will do more reactions than saturated compounds. So first of all, let's review how we name organic compounds. You should remember from O level that we said anything that has one carbon, its name should start with meth. Two carbons, the name starts with F, prop, but, pent, hex, and then the remaining of the name would either be ane or ene, depending on the type of compound or the functional group present. We also know here in this syllabus that you should know that if we have a chlorine somewhere, this is called chloro something, or bromo something, or iodo something. If I have an NH2 on a compound, that is an amino group. If I have an NO2, it's a nitro group. So let us see how we name organic compounds. So this is something you should know from O level. To name the compound, I first count the number of carbons. Now, how many carbons do I have here? I have 2. And you should remember that anything with 2 carbons, the name should start with what? With F. Now, I look at this compound and I determine, is it an alkane or alkene or alcohol or acid, depending on the functional group present. This is something that has an OH, so it's an alcohol, so we call it ethanol. Okay, this one the same thing. So what's the number of carbons? It's 4 carbons. 4 carbons should start with but. Now it is but what? Well, it has a double bond somewhere, so it's an alkene, so it's called butene. And I need to specify where the double bond is. You can see that the double bond is after the first carbon, so I call it 1-butene or but-1-ene to indicate the presence of the double bond. This one is just something that has 2 carbons. Also, the name should start with F. It has only single bonds. It's not an alcohol. It's not an acid. Just has single bonds, so it's an alkane. So this is just ethane. You remember all of this from O level? You should. Now, this one is something that has 1 carbon. 1 carbon, the name should start with meth. Now, it has double bond O, single bond OH, and if you remember from O level, this is an acid, so this is called methanoic acid. That's how we name the acid. Okay, now, the new thing this year is if I have a branch chain like this. Now, how do I name this? How many carbons do we have? Well, I should first of all try to find where is the longest chain. Longest chain means carbons one after the other that give me a higher number of carbons. So if you look at this is how we can count the number of carbons. So this is 1, 2, 3, 4, 5, 6. So this is a hex something. Now all of them are single bonds, nothing else. So this is a hexane. But then I have branches. Can you see the 3 carbons that are attached to that chain? I need to indicate, first of all, this is a C with 3 H's. So this group is called methyl group. And they are on which carbons? Now we count from the side that gives the lower number of carbons. So I count from that side, that would be carbon number 1. Then the methyl groups will be on carbons number 2 and 4. If I count from the other side, the numbers will be high. So how do we name this? This is 2,2,4 trimethylhexane. Again, the longest chain has 6 carbons, so that is hex. The compound is an alkane, so this is hexane. Now, what kind of substituents do I have on this chain? I have 3 methyl groups, so that is trimethyl. Now, what is the position of the methyl groups? I have 2 of them on carbon number 2, so that means I have 1 on carbon number 2, another one on carbon number 2, and a third one on carbon number 4. So this is how we write its name. Are we following? I hope so. Then we have different types of formula. Now, in O level, we had only 2 types of formula. We had displayed formula, where you show all the bonds with all the atoms showing. So if I'm drawing the displayed formula of ethanol, this is how I would draw it. But then we also have something called the structural formula. A structural formula is where I take each carbon and determine how many hydrogens around this carbon, and I sort of collect them together. So that first carbon has 3 hydrogens, the second carbon has 2 hydrogens and an OH, so that would be the structural formula. You already know that the molecular formula is the total number of carbons, total number of hydrogens, and oxygens. So the molecular formula for ethanol would be C2H6O. But we also have something called skeletal formula. Skeletal formula is just drawing lines. You do not draw any carbons or hydrogens. Now, when we draw any of these lines, at the end of each line, it is understood that you have a carbon, and then each carbon will have the required number of hydrogens so that it has a total of 4 bonds. Remember that carbons have 4 bonds. So this is how we draw propanol, for example. I have 3 carbons and then an OH. Propene, I have 3 carbons and 2 of them have a double bond between them. Propanoic acid would be the 3 carbons with double bond OH. So if we try to name this, for example, again, we said to name it, we need to choose the longest chain. So where is the longest chain? That is the longest chain. So that is 1, 2, 3, 4, 5, 6 carbons. So that is a hex, and it's an alkane, so hexane. I have 2 methyl groups attached to it, and we said we count from the side that gives us the lower number. So this is 2, 4 dimethyl. I have 2 methyl, so that's dimethyl hexane. Please practice these names. Okay, we have different types of isomers. And you should remember from O level that an isomer is 2 or more compounds having the same molecular formula but different displayed formula. That means I have the same molecular formula, same number of carbons, same number of hydrogens, and so on, but different displayed formula. That means different structures. Now, we have one type of isomer which is chain isomers. And the chain isomers just indicate that I'm going to put things in different positions. So, for example, if I'm trying to draw propanol, you should know propanol is something that has 3 carbons. All means the OH is on one of them. Now, where am I going to put it? On the first carbon? Remember that we count from the side that gives you the lower number. So that first structure is 1 propanol, not 3 propanol. We count from one side, it's 1, from the other side, it's 3. So I count from the side that gives me the lower number. So here I have the OH in 2 different positions. So one of them is 1 propanol and the other is 2 propanol to indicate the different positions of the OH. Another example of chain isomers would be isomers of an alkene like butene. Now, you should realize but has 4 carbons. Ene means I should put a double bond somewhere. Now, where am I going to put it? That's the different isomer. So if I put the double bond after the first carbon, so that is but1-ene or 1-butene, remember? So the 1 indicates the presence of the double bond. Now that other structure, the double bond is after the second carbon, so that is but2-ene. So these are examples of chain isomers. Also, if I want to write an isomer of an alkane, now remember, when we were writing isomers of alcohols, we put the OH in different positions. Isomers of butene, we put the double bond in different positions. Now, if I'm doing isomers of butane, it's an alkane. So to draw the isomers of an alkane, I just put them in different chain lengths. So if I have C4H10, I can either put the 4 carbons all after each other, so that is a straight chain, or I can put 3 carbons and put a methyl group, a CH3 group, on the middle carbon, so this is what we call a branched chain. Isomers of pentane would be the same way. Pentane means I have 5 carbons, so I can either put the 5 carbons in a straight chain or one of the carbons as a branch or 2 of the carbons as a branch. So these are 3 isomers of pentane. But another kind of isomer that we did not do in O level was geometrical isomers. Now, geometrical isomers are isomers that indicate that I have a double bond between the 2 carbons, and each of the carbons that are on both ends of the double bond have different groups. So, for example, these 2 structures have a double bond between 2 carbons, and each carbon has 1 methyl, 1 hydrogen, 1 methyl, 1 hydrogen. So each carbon has different groups. Now, when we have different groups like this, you can either put the 2 methyl groups on the same side of the double bond, or the methyl groups on different sides of the double bond. And these 2 are what we call geometrical isomers, and these are 2 different compounds because there is restricted rotation around the double bond. Now, what does that mean? If I have an alkane has only single bonds, and the single bonds can rotate around each other. So I can just change the compound, that red ball, up or down, it can change. That means that I can rotate them around each other. This is because they have only single bonds. If they have a double bond, they cannot rotate around themselves, so they are fixed in a certain configuration. So that means they are different isomers. So for example, if I have, this is butene, butene has 4 carbons. This is but2-ene, the double bond is after the second carbon. Now, if I have both methyl groups on the same side of the double bond, this is what we call a cis isomer or a Z isomer. So in the cis or Z isomer, the substituents with higher molecular mass are on the same side. So if I'm looking at that first carbon of the cis, the carbon is attached to a hydrogen and a methyl group, the CH3 group. Now, which one has higher mass, atomic mass, the hydrogen or the carbon? We know that the carbon has the higher atomic mass, so that is what we call the first priority. Now, the other carbon on the other side of the double bond also has the carbon on that side of the double bond. So both the ones with higher priority are on the same side. This is called a cis isomer or a Z isomer. If the 2 methyl groups are on opposite sides of the double bond, this is called a trans isomer or an E isomer. So in order to determine if something is a Z or an E or a trans or a cis, then we look at the priorities of the masses of each one. So for example, bromine and iodine, which one has higher molecular mass or atomic mass? that is iodine. Iodine has higher atomic mass. Now, on the other side of the double bond, I have a fluorine and a chlorine. Now, which one has higher atomic mass? It is chlorine. So, iodine and chlorine are on the same side of the double bond. This is what we call a cis or a Z. The other one, the bromine and chlorine are bromine and well, we have iodine on one end, that is higher molecular mass. Chlorine on the other end is higher molecular mass. So they are on opposite sides of the double bond. So that is a trans or an. Do we understand this? So this is the same thing. We look at each carbon with a double on one end of the double bond. This one has one carbon, the other has two carbons. So the one with the two carbons has higher priority. Now on the other end of the double bond, there is a Cl and there is a COOH. That means the Cl and the Cl is higher priority. Now that means that this is a trans or an E. The other one will be a cis or a Z. Okay, you should remember that all organic compounds are obtained from petroleum. This is done by, first of all, fractional distillation of petroleum or crude oil. So the crude oil is heated and vaporized and then condensed to give different fractions at different boiling points. So if you remember from O level, we said we heat the crude oil, pass it into a fractionating column or a fractionating tower, and the different fractions are uh, cooled and condensed at different boiling points. The one at the top is the one with the lower number of carbons, lower boiling point. Next, we take these fractions and then we do what we call cracking. And you should remember that cracking is the breakdown of a long chain hydrocarbon into shorter chains. This is done using 600 to 700 degrees centigrade, or you could just see very high heat or lot of heat, and a catalyst like aluminium oxide, or we said silicon dioxide can also act as a catalyst. So we said when we do cracking, we have something with a large number of carbons. So let's say I'm starting with hexane. Now, when we do cracking, under these conditions of 600, 700 degrees Celsius and aluminium oxide catalyst, we either get an alkene and alkane or an alkene and hydrogen. So we said this is a method of making hydrogen. This is how they manufacture hydrogen. Now, of course, cracking is important because this gives shorter chains, and shorter chains are usually more flammable, so more in demand, more economically important. It is also used to manufacture hydrogen gas, and one of the products is usually ethene, and ethene can be used to make ethanol and polymers. A third process that can happen is reforming, and you should remember now that reforming means if I have a straight chain, I can change it into a cyclic compound, or I can change it into a branched compound. This process is called reforming. So reforming is a process that converts the straight chain hydrocarbons into branched or cyclic compounds. We need this because usually the branched chain alkanes will burn more efficiently, or it will have more efficient combustion. So that is the advantage of doing reform. Again, you should remember alkanes are saturated, and we said they're saturated because they have only single bonds. They are hydrocarbons because they all have carbon and hydrogen only, and their general formula is CnH2n plus 2. That means the hydrogens are twice the number of carbons plus 2. And we said I can either draw the alkane in a displayed formula, or a structural formula, or a skeletal formula. One of the important alkanes is methane. This is because methane is the main constituent of natural gas. So when we use natural gas as a fuel, actually the natural gas is mainly methane, so it is used as a fuel. You probably remember from the previous chapters that we did that the geometric structure of methane is that it is tetrahedral because it has four single bonds or four bonding pairs of electrons, and the bond angle is 109.5. Now, reactions of alkanes. Reactions of most of the organic compounds involve combustion. So, and you should realize that combustion means burning in oxygen. And we said we have two types of combustion. Either we're talking about complete combustion in which there is excess of oxygen. In that case, carbon dioxide and water are formed. Or if we have lack of oxygen, or what we refer to as incomplete combustion, then this will form carbon monoxide plus water, and you should remember that we said carbon monoxide is poisonous or toxic. And the combustion of alkanes is a problem. So combustion of what we call fossil fuels is a general problem for the climate and for the environment, because we just said it forms carbon monoxide. This is a toxic gas. It also forms other gases like oxides of nitrogen and sulfur oxides that cause acid rain. And you should remember that acid rain kills plants, dissolves limestone in buildings, so this causes buildings to crumble. It can also form particulates of carbon or pieces of carbon that float around in the air and irritate the respiratory system if you breathe them in, or they can result in unburned hydrocarbons. So all of these are harmful to the environment and to our general health. So now they are doing alternative fuels. The kind of alternative fuel that is now being preferred is what we call biofuel. And biofuel is fuel obtained from remains of plants or animals. So if we have fossil fuel is obtained from petroleum, but biofuel is obtained from plants or parts of animals. So what we call bioethanol is actually an alcohol that is made by fermentation of sugar. So we get sugar from sugar cane, and then we do fermentation and get ethanol. So this is referred to as bioethanol. Or if we have vegetable oils or animal fats, we can obtain what we call biodiesel. So these are called biofuels because they are obtained from living organisms, plants or animals. And these are preferred, biofuels are preferred to burning of fossil fuel because we refer to them as carbon neutral fuel. Carbon neutral means they do not affect the level of CO2 in the air. This is because they're obtained from plants. And you should realize that plants, while they are growing, so trees that are growing, take up carbon dioxide by photosynthesis. Now, when we take from these plants, we take wood or we take bioethanol or whatever, these burn and release the carbon dioxide back into the air. So actually, the carbon dioxide that is released into the air is something that was already taken up from the air during the growth of the plant by photosynthesis. So there is no net increase in carbon dioxide in the air. So it is not just putting carbon dioxide into the air. So we say they are carbon neutral fuel. The advantages of using biofuel, of course, is that it will give less carbon dioxide, so less global warming, less sulfur dioxide, so less acid rain, and of course, growing crops for fuel creates new jobs. But on the other end, there are disadvantages to the use of the biofuel because instead of using the land for food, to grow food, we're using the land to grow things that are going to be used for fuel. So this is using up the land. So this is reducing the food supply. This may lead to deforestation, loss of habitat, because we are going to cut down the forests in order to grow the plants that we need for the biofuel. In addition, if I need to use this biofuel, I need to adjust or modify the cars in order to be able to use these biofuels, and this might be costly. So these are disadvantages of the use of biofuels. Now, another reaction of alkanes is substitution reaction. And you should realize the substitution reaction, first of all, is alkane. So alkanes are the ones that do substitution. And in substitution reactions, they're reacting with halogens. Now, in order to react, we said alkanes have only single bonds. They're not very reactive. So we need to start the reaction using UV light. So the condition that starts this reaction is ultraviolet light. What happens is we remove one of the carbons that is on the methane, replace it with one Br, and my other product will be the hydrogen that I removed plus the other Br, so that forms HBr. So this is called substitution reaction of alkanes. Now, it is very important to know the mechanism of this reaction. He will ask you to write at least parts of this mechanism. So overall, what are we doing? We're trying to react methane with chlorine to form what we call methyl chloride, CH3Cl plus HCl. Now, how does this happen? This happens in three main steps. The first step is called initiation step. And for this to happen, this is where I need my UV light. So the UV light acts on the chlorine and breaks that bond so that the paired electrons, each one goes to one of the chlorines. So I have a bond between the two chlorines. These are made up by sharing of a pair of electrons. Now, when the UV light breaks this bond, one of these electrons goes to each chlorine, and that means that I have this half arrow. Can you see the half arrow there? This half arrow indicates I have only one electron going to each chlorine. This results in what we call a free radical. So that thing with the dot on it is called a free radical because it has one electron standing there doing nothing. It's called an unpaired electron. So free radicals are species that have an unpaired electron. Now, this Cl dot or Cl radical now goes on to do something which we call propagation steps. It attacks one of the methyl groups, removes one of the hydrogens, and forms a methyl radical plus HCl. Now, this methyl radical, all free radicals are very reactive species. So this methyl radical reacts with another chlorine molecule, breaks it up to form a chlorine radical, which then goes back and reacts with a methane group, and so on. And this is what we call propagation steps. They keep going on and on and on until two radicals join together. If two radicals should join together, that will end the reaction, and that is called a termination step. So either we have a CH3 radical with CH3 radical, so that forms C2H6, or a chlorine radical with a chlorine radical, this forms Cl2, or a methyl radical with a chlorine radical, and this forms CH3. And once these termination steps happens, the mechanism ends. So this is a free radical substitution mechanism, and you need to know how to draw all of these steps. You should realize that when we talk about breaking up of bonds or bond fission, we can have two types of breaking up of bonds or two types of bond fission. One of them is referred to as heterolytic fission. Heterolytic means both electrons that are being shared will go to one of the atoms, leaving the other lacking electrons. So when both electrons go to B, for example, now B has an extra electron, so it's a B minus, and A is now lacking an electron, so that is A plus. So most of what we have been talking about in reactions previously in O-level or in most of the reactions that we talked about, these are heterolytic fission in which, for example, sodium chloride forms Na plus and Cl minus. Now, remember that a species that has A negative charge can act as what we call a nucleophile, and something that has a positive charge can act as an electrophile. Now, what's a nucleophile and what's an electrophile? A nucleophile is something that has extra electrons, so it can attack a carbon atom. And something like OH minus, Br minus, Cn minus are referred to as nucleophiles. So when they react, they give their electrons to the carbon atom. Electrophiles are species that take a pair of electrons. So a nucleophile has a lone pair of electrons, while an electrophile has um, less electrons and can accept electrons from some. Another type of bond fission or bond breaking is homolytic. So when we talked about this in the mechanism for the free radical substitution, we said one of each electron goes to one of the atoms and forms free radicals. This is an example of what we call homolytic fission. And the free radical that is formed has an unpaired electron and it is very reactive. It will react immediately. Okay. Alkenes, remember, are unsaturated, and we said they are unsaturated because they have a double bond between the carbons. The general formula is CnH2n, and they are very reactive due to the presence of the double bond. This is because the double bond is made up of two bonds. One which we refer to as sigma and one which we refer to as pi. Now, the sigma bond is due to overlap of the s or the p orbitals head to head. So it is an overlap that is very strong and does not break easily. But the pi bond is formed when the p orbitals overlap side by side, and that's a weak overlap. So the bond here is weak and it can be easily broken. So when an alkene reacts, it is the pi bond, which is made up of the two clouds of the p orbital, that is broken, not the sigma bond. The sigma bond is very strong and does not break easily. So again, let's talk about the reactions. Now, reactions of alkenes, we said burning just like alkanes, whether they are complete combustion to give carbon dioxide and water, or incomplete combustion to give carbon monoxide and water, and the carbon monoxide is poisonous. Now, remember when we were talking about alkanes do substitution reactions. But alkenes do what we call addition. Addition means we're not removing anything, we're just adding to the compound. So if I have ethene, I react it with Br2. Now we said the double bond breaks up to form a single bond, and we add something on both carbons that have the double bond. So here I'm reacting with Br2, then that means I have Br and Br. This is used as a test for alkenes. If you remember from O level that we said tests for alkenes was add bromine water. The color changes from reddish brown to colorless. This is because when I react with bromine water, the double bond breaks up. Please notice the double bond will break up and form what? It will form one Br and one OH. So this is the product formed when I have bromine water. We said if I'm reacting it with just bromine, or what we call bromine liquid, this will form Br and Br. But if it is bromine with water in it, aqueous bromine, then it will put a Br and an OH. Another addition reaction, remember all of these are types of addition reactions. So when I'm adding hydrogen, this is called hydrogenation. Remember the conditions. If I'm adding hydrogen, hydrogen will need a catalyst like nickel, or sometimes we use platinum, and we will also need heat. So it is 180 degrees Celsius or heat and nickel catalyst. This will open the double bond, put a hydrogen and a hydrogen on both carbons. Now, if I'm reacting with water, this addition reaction is called hydration. So it's a type of addition reaction where I'm adding water. You have to remember the conditions. The conditions are I should use steam, or we say we put water at 300 degrees Celsius. So you can either say that you added steam or you added water at 300 degrees Celsius. And we need a catalyst, which is usually phosphoric acid catalyst, H3PO4. That will open the double bond, put an H on one carbon and an OH on the other. Hydrohalogenation means I'm reacting it with HBr or HCl. This is done at room temperature, so you don't need any other conditions. You open the double bond and you put the Br on one carbon and the hydrogen on another. Now, what is the mechanism of this? The mechanism of this is called electrophilic addition. Remember when we were talking about substitution of alkanes, we were saying this is called free radical substitution. Now we're talking about addition of alkenes. This is called electrophilic addition. Now what happens? The bromine actually becomes polarized, so it has a slightly positive end and a slightly negative end because the electrons from the double bond attack one bromine. So this repels the electrons to the other bromine and it breaks the bond. So I have an arrow coming from, this is called an arrow coming from the double bond to the first Br, and then another arrow coming from that bond between the two Brs going to the other Br. So I end up with a Br that has electrons and a total negative charge. Please notice the difference between a slightly negative charge, that's a delta with a minus, or a full negative charge. So at the beginning I have Br2. In the Br2, each one of them has slightly positive, slightly negative. The double bond attacks the Br with the slightly positive. The bond between them, electrons will go to the Br that's slightly negative. Now, that gives me a Br with a full negative charge and extra 2 electrons. So these attack this carbon atom that has a positive charge. The carbon atom that has a positive charge on it is called a carbocation. So the Br minus attacks the carbocation and forms the product. Now remember, the first step where I have the double bond attacking the Br2, in this case the Br2 is acting as an electrophile. Remember we said electrophile means something that accepts electrons. So it is taking the electrons from the double bond. In the second step, the Br minus is attacking the carbocation, so the Br minus is acting as a nucleophile, and we said a nucleophile is something that has extra electrons. Now, where do I put the hydrogen and where do I put the OH, or where do I put the hydrogen and where do I put the Br? This follows what we call Markovnikov's rule. When we have something like propene and we have something like water, which is HOH or HBr, there are two possibilities. Either, remember that the water breaks up to form H and OH, so I'm supposed to add H and OH to the two carbons that have the double bond. Now, where am I going to put them? Will the OH be in the middle or the OH on one end? They found, or Markovnikov's rule says, that the OH will be on the middle carbon, and that will be my major product, while I will have a little bit of the product with the OH on the end, and that is a minor product. Now, why is that? You should be able to explain that. If I'm reacting, for example, the double bond with an HBr, the H is slightly positive, the Br is slightly negative. Now, we said we're going to form a carbon with a positive charge on it, which we called a carbocation. Now, you should realize that this carbocation in the middle is called a secondary carbocation. So, a secondary carbocation is one in which the carbon with the positive charge is attached to two other carbons. So the secondary carbocation is more stable than the primary carbocation. If I added the H on the middle carbon and left that carbon at the end with a positive charge, that is called a primary carbocation, and that is less stable, less likely to form. So I end up with the product with the Br in the middle as a major product. Are we all following somewhere? Okay. Oxidation reactions with potassium permanganate. You should realize that if I have a double bond and I add cold acidified potassium permanganate, so my reactants here are actually potassium permanganate and sulfuric acid, and this is cold, I'm not heating or anything, the double bond opens up and puts an OH on both carbons that have the double bond. This is called a diol. Something with two OHs is called a diol. So remember that reaction with acidified potassium permanganate or potassium manganate with concentrated sulfuric acid, this will give a diol. That means I'm going to open up the double bond and put an OH on each carbon. The last part of this chapter is polymers, and you should remember from O-level that polymers are large molecules made by joining many small molecules together. The small molecules are called monomers, the large molecules are called polymers, and the process of joining these small molecules to form a large molecule is called polymerization. Now, why do we need polymers? We said polymers are basically what we call at-home plastics. So what do we use polymers for? Well, whatever we use plastic for. So we use it to make plastic bags, plastic bottles, plastic chairs, plastic ropes, whatever. The problems of the use of polymers, if you remember, that we said polymers are non-biodegradable. That means they are not broken down by bacteria, and if they are non-biodegradable, they accumulate in dump sites. So when they're thrown, plastics are thrown in the dump sites, they remain there for years. Or for now, we see that they accumulate even on places like beaches or on the ocean. We have a lot of plastic accumulating everywhere. This is because they are non-biodegradable. Now, even if we try to burn them to get rid of them, that results in toxic gases. So we cannot even burn them to get rid of them. So this is the problem of using polymers. Now, chemists are now trying to overcome these problems by trying to develop biodegradable polymers or to remove the toxic waste gases that are produced when burning polymers. You should know that there are two types of polymers. We have what we call addition polymers, and these are if I'm starting with an alkene. So if I'm starting with something that has a double bond, then the polymer I'm forming or the type of polymerization I'm forming is addition polymerization. If I have polymers in which the small molecules have small functional groups on both ends, then we are talking about condensation polymers, and we will not be talking about that in this unit 1 of the AS chemistry. So what we will be talking about is addition polymers, and you should remember how to draw an addition polymer. We said polymers means I have many of the monomers. So I have many molecules of ethene and I'm trying to join them together to form a long chain. Now, in order to break it to form a long chain, we said it's the double bond that will break to form a single bond. And then we're going to form bonds on both ends to join them to molecules before and after them, because we have many ethenes joined together, and this part will be repeated many times. And we said if my monomer is ethene, the polymer will be called poly, that same name, polyethene, even though it doesn't have a double bond anymore. But this is just referring to the fact that it is a polymer of ethene. Again, if I'm trying to draw the polymer for propene, we said we look at the double bond. We don't look anywhere else. The double bond breaks up to form a single bond. A bond forms on both ends to join them to molecules before and after them. And we see each carbon was originally bonded to what? So the first carbon was bonded to a hydrogen and a hydrogen. Now that second carbon on the other end of the double bond is bonded to one hydrogen and to a carbon that's bonded to three hydrogens. So this is what the polymer looks like. Remember, sometimes he will tell you draw the polymer, so that's it, or draw it in the form of an equation. In that case, you will have to indicate that I have N of propene, so I should write a small n in front of propene to indicate that I have many, a certain number which I don't know which number, so we say it is N. So I write N of propene, N of that molecule, then an arrow, and I write the polymer. And sometimes he asks me to write the polymer 2 repeat units or 3 repeat units. You just repeat that part 2 times or 3 times. How to draw a polymer of 1-butene? Again, we look at only the 2 carbons that have the double bond, change it into a single bond, a bond from before and a bond after to join to the molecules before and after them. And then you look at each carbon and you see it is bonded to what. So that first carbon is bonded to a hydrogen and a hydrogen. The second carbon on the other end of the double bond is bonded to a hydrogen and bonded to all that group, 2 carbons with 5 hydrogens. Butene, I look at the 2 carbons that have the double bond. I write them with a single bond, bond on this end and bond on the other, and then I see each carbon that had double bond was bonded to what. So this first carbon is bonded to a hydrogen and a carbon that has CH3. The other one is bonded to a hydrogen and a carbon that has CH3, so I end up with that product. This is the same as what we did for O-level. Vinyl chloride also is something that has a double bond. You also draw it in the same way. The double bond becomes a single bond, bond on either end to indicate that we are joining it to other molecules similar to it before and after. And each carbon, the first carbon was bonded to a hydrogen and a chlorine. The second carbon was bonded to 2 hydrogens. So that is what your polymer will. Okay, thank you for listening. I hope this video helps you when studying for the S chemistry, and we'll meet in another video. Thank you very much for listening.